Swayam Prabha. Digital India. Educated India.
Good afternoon for this mock course on fluid mechanics. Today I have very interesting class on blackboard, solving the problems on Bernoulliâ equations applications. Before starting this class, as usual in the next class where we discussed that we are following these three books, Sinjal Simbala, F.M. White and Vidyasagar Pani, and today we'll focus more on solving the GATE exam questions. As we start with a real life example problems, today let us start with a real life problems like estimating the wind loads of a building where the cyclone effect is more disastrous. So for example, if you look at the airport locations in Bhubaneswar and the cyclonic speed of the 250 km per hour, you can compute it what will be the pressure difference between the upstream in off area as well as the inside the airport, and that pressure difference will uplift this the roof of this airport system. So basically what I'm to try to say that if you look at these problems, which look it's very complex, but with help of the control volume concept and the drawing the streamlines, we then if you apply the Bernoulliâ equations, you can solve these problems to estimate what could be the wind loads when you have a cyclonic speed 250 km per hour passing through this type of civil engineering structures. And if you look at this way, it's quite easy to compute the wind load estimations, but we should know exactly how to apply the Bernoulliâ equations and what are the assumptions are there, how we can make a very complex problems in a simpler way by following the control volume concept, pressure diagrams, velocity diagrams, then applying the Bernoulliâ equations. So in this class, I'll talk about three basic equations what we have derived in the last class. Those equations, again I have to repeat it. Like if you look at that, this mass conservation equations, which are very basic equations. If you look any control volume, we consider it that this is a change in the mass storage and this is mass outflux, influx. That's what is should equal to 0. This is what the mass conservation equations. But if you simplify that, it can come out to be Q1 is equal to the Q2 with there are certain assumptions like the steady flow, there one-dimensional flow, then mass inflow is equal to the mass outflow. Similar way, if you look at this momentum equations what we derived earlier, and that what will be expressions like this. So what you supposed to do it whenever write this type of big equations, try to write this all these dimensions and check it the dimensions of each components whether they are the equal, and from these dimensions you can understand it what is this component is indicating. Like for example, for this case it's a mass flux, mass per unit time. In this case, if you look at that, this is what the force components, ML T minus 2 is the force components. So each components representing as a force components. That's what we try to understand by writing the proper equations for conservation of mass and the linear moment. And if you look at that basic equations of Bernoulliâ equations, which has the pressure head component, the velocity head component and the elevations head, those what if you include it as the flow energy per weight, the kinetic energy per weight, and the potential energy per weight. That's what the unit wise is, each one is in a meters, is equal to constants along a streamline. That's the basic assumptions what we have for the Bernoulliâ equations. Let us solve the 5 questions from GET question set. The first examples, one, what I have considered it, the circular water pipes shown in the sketch are following full condition. The velocity of the flow in the branch pipe are each. That means let's sketch the figure first. That there is 5 connections like this. This is what, 4 meters, and these dimensions is 2 meters, and we have the velocity here, v is equal to 6 meters per second, and the velocity at this point v equal to 5 meters per second, and we need to compute what is the velocity at this point. So if you look at these problems, it's very simple problems of mass conservations. But before solving these problems, let us tell it the stepwise. After this sketching the problems, please draw a control volume. Draw a control volumes. And from these control volumes, you can identify, this is what the control volumes, you can identify the inflow regions, the outflow regions, where is no flow regions. We should identify it. So once you identify, sketch the control volume, sketch the control surface, identify the pressure, the control surface and the flow directions. In this case, we can have the assumptions or the flow classifications is that first it is the one-dimensional flow. Flow is the turbulent flow. And here we can consider the flow distributions is uniform flow velocity distributions. Once you have these assumptions, the problem is quite simplified for us. And the fourth one, we can have the steady flow. So please remember that whenever you draw the control volumes, you first classify the flow. First is one-dimensional flow, turbulent, steady, it doesn't vary with the time, and the uniform flow distributions. That means the beta is equal to 1. Then we will go for the what are the data is given. It's given data set. In this case, it's a very simplified case that if I find out the velocity in V1 and V2, and this is the V3, so I have the velocity V1 is 6 meters per second, V2 is equal to 5 meters per second, and D1, the diameters is here 4 meters, D2 is also the 4 meters, but V3 is unknown to us, and D3 is 2 meters. The problems, if you look at it, you can write the given data sets like this, so that from this control volume, you can find out what is the V1, V2, D1, D2, D3 needs to be computed, and this D3 is given to us. Then we go for applying simple mass conservation equations. When you apply the mass conservation equations, you can start writing the mass conservation equation from basic RTT levels. Then you simplify the terms one by one. Like if it's have a one inlet in this case and two outlets. So what we have, that we are just applying the mass conservation equations for these simplified the control volume concept. The mass conservation equations, if you look at, we will have a okay. Just you look at these equations. This is changing the mass storage within this control volume. This is what the influx mass. These two are the outflux mass. So rho A into V, that is what the mass flux. Rho A2 and B2. This is the mass flux outgoing in the A2 die. Similar way, we have the rho A3 V3. So in this case, as it's a steady flow, so these components becomes 0. So we have only these three components what we need to compute it. And as the rho is a constant, or since it's a only water is flowing through this, so we can easily compute it that the A1 V1, A2 V2, A3 V3 is equal to 0. So you just substitute the velocities and the area of the flow at A1, A2, A3 will compute the V3. That's what is going to come 4 meter per second. So the numerical value, I am not putting it individually, but please put it, then you will get the solution V3 is equal to 4 meter per second. More details we will provide in the slides. Let us start the question, example number 2, in which a tank deflectors are placed on a frictionless trolley. This is what frictionless trolley. That means there is no friction force components are there. The water issues a water jet. This is what the water jet, and that which strikes the deflectors turns 45 degrees, and if the velocity of jet leaving the deflectors is 4 meter per second, the V jet is equal to 4 meter per second, and the discharge, the Q, is equal to 0.1 meter cube per second. Then we have to find out what could be the force acting on this spring. This is what the problems. If you look at these problems, even if you look at complex things having the trolley, the water tank, the deflectors and the spring, but it's a very easy problems because we need to compute what will be the force acting on this spring. So first you sketch the problems, then do the flow simplifications, okay, or the flow classifications. So in this case, if you look at, we can assume it's a one-dimensional force component as we sketch the control volumes like this. Okay. So once I sketch this control volume like this, if you look at it, that technically there is no flow anywhere except there is a flow jet which is going out from this. Okay, that's what is happening. This the water jet is going out from this for this control volume, but there is a force component why it is acting on this, the spring part, which is the Fx part, and there is no frictional forces, so there is the force component at this is equal to the 0. So there is no force components what is there over this the control surface, and only this water jet is going out from this for this the control volume. Now we can simplify these problems as we classify the problems like these problems. Also we can say it's a one dimensional as we have the water jet problems. Secondly, have the steady flow. It could be the turbulent the flow conditions, but what we have considered is a fixed control volume. We have considered fixed control volume, and over this control surface everywhere the pressure is equal to P atmospheres. So that means we needed to consider the pressure diagram for this case, as the pressures everywhere except these jet locations the pressure difference are there, but other surface is pressure is equal to the atmospheric pressures. So looking this part as it is a fixed control volume, we can write the basic equations. Before that, as this flow distributions what is there, the velocity distributions for this small jet what is going out from this, we can consider as a uniform flow velocity distributions. As you consider it's a uniform velocity distributions, the momentum correction factors beta becomes 1. So this is quite simplified, and that's the conditions happens when you have a water jet is going out. There could be the velocity distributions there, but the assumption of uniform velocity distributions also quite valid for this type of calculations. Now let us have the data given here, given data set. One is the velocity, jet velocity, the discharge, the Q values. Second is that the deflected angle. In this case, it's a 45 degree. Okay. So in this case, if you look at these problems, it's quite simplified problem, because we needed to apply any mass conservation equations, because we just need it what could be the force acting on this spring. That means it's quite easy problems. Just we have to apply linear momentum equations for these control volume. Let us write the linear momentum equations for these control volumes. Then we will simplify the linear momentum equations to get the solutions for this. So linear momentum equations, if I write it from the applying Reynolds transport theorems for the control volume, we'll get it that dy dt of system, that's what equal to the sum of the force acting on this will be control volume control surface this is what, if you can remember it, the Reynolds transport theorems, the sum of the force acting on this control volume said is equal to the rate of change of the momentum flux within the control volume, net of the change of the momentum flux passing through this control surface, the net momentum flux, that's what will be equate for this case. So if you look at this case, this is becomes 0 as it the steady flow conditions. This components becomes 0. So only you have a sum of the force components and the momentum flux through this control surface. That's what we need to put it. So in this case, if I put the along the x-axis, if I write these equations, then Fx will be equal to sum of momentum flux out beta m dash v average minus beta m dash v average as in. So in this case, as the beta becomes 1, the mass flux in and out. So in this case, there is a no influx. That's what this is equal to 0, and the force components will be the only this component. Only this component. So we can easily resolve this component. The sum of the force acting for this case will be equal to m dot z v cos theta. The mass flux will be the rho into q v cos theta. Now you substitute the value of Vz, that's what it will be, z, theta you know the 45 degrees and you know the q value. If you substitute it, and the values what will come it 282 Newton. So this way we can solve these problems. Let me highlight that way, that first you draw the control volume. Once you draw the control volume, try to find out what could be the pressure distributions. Whether we can neglect there is a pressure difference at the water jet part, and then you look at what are the mass influx and outflux is going out, or momentum flux going in or coming out from the control surface. Once you conceptualize that, then you apply. In this case, we just apply the linear momentum equations because mass conservation equation is not required for this case, and using this the appropriate assumptions, we've simplified this Reynolds transport equations to very simplified the force component along the x directions, and this force component will be equate with the force component acting on this. That means the force acting at the spring, that's what will become this value. So you can use the linear momentum equations to solve this type of the problem. Let us go for the example 3, which is about the water flow through a 90-degree band in a horizontal plane as given in the figures. The pressure at 140 kilopascal is measured at the section 1-1. The inlet diameter the section is 27 by square root of 5 centimeters, where the nozzle diameters marks as sections 2-2, which is 14 divided by square root of the 5 centimeter. Find the magnitude of the force in kilonewton that could be required to hold these pipe sections. So if is that problem, let us first sketch this problem. The problem is there is nozzles and this making like this surface. So it has a sections 1 and sections 2. This is inlet, this is the outlet. The pressure at the inlet 1 is given at 140 kilopascal. Pressure at 1 is given as this, and the 5 inlet diameters D11 is given as 27 by square root of 5. At the D2 section 2 it's given as 14 by square root of pi. So the question is that how much force would be required to hold this pipe. Okay. So if you can understand from these problems, as the flow is going here and we are deflecting a 90-degree band. This is what? The 90-degree band. There will be a change in the moment of flux, the direction. That's what will be exerted force on the 5. So if you look at these problems, it's a quite easy problems to find out what will be the force components, as if I give it 2 directions is Fy and Fx. What will be the force component acting on this, the 90-degree bent part? So first what you have to do is to draw a control volume. Draw a control volume, and you have a external force acting on this is Fx and Fy. And here you have everywhere you have pressure equal to atmospheres. At this point you have a pressure is equal to atmospheres, but at this inlet point you have a pressure which is 140 kilopascals. So you know the pressure diagrams. You know the pressure diagrams. You know this control volume. And here you have the velocity, the flow velocity is there, and here also you have the flow velocity component is there. If you look at these control volumes here, you can easily know it because there is one inlet and one outlet. You can define that Q amount of discharge if it's come into this and going out, the same Q will commit here. So the problem is here, the Q11 is equal to Q22. That's what will be Q. This is what the mass conservation equations, which is indirectly implemented in this case, as there is a one inlet and one outlet case. So Q is constant here. So if you have a Q is a constant, I can draw a streamlines. I can draw a streamline here. I can draw a streamline, and along these streamlines, at these 2 points, at 1 section and the 2 sections, we can apply the Bernoulli's equations for this case. So the assumptions what we have done it are the flow classifications. Flow is one-dimensional flow, steady, turbulent, and we have consider no frictional loss, or we have neglected the frictional losses, what will be there because of pipe water flow through these nozzles. That's what we have considered. There is no frictional losses, or frictional loss is not that dominated as compared to the force component what is acting on this. So if you have this case, so first you have a mass conservation equations, you have applied it here. Now I am going to apply to compute what could be the Q value. We are applying the Bernoulli's equations. We are applying Bernoulli's equations. As I have drawn the streamlines following through this path, I can just apply the Bernoulli's equations at the section 1,1 and the sections 2,2. Section 1,1 to section 2,2 along the streamline. If I apply that, then what I will write it? P is equal to P2 or we can write it here in terms of Q. In terms of Q, we can write same equation, Q square by 2G A1 square P2 2G A2 square. You know it. The Q will be the A1 V1 A2 V2. That's the equations, the continuity equations. That's what we applied it. Since it's on the horizontal surface, you can consider Z1, Z2 equal to Z value. That's what we will cancel it. We know this, the pressure values here. We have to compute now. We know this A1 value, A2 value. We have to compute what will be the Q value. From this, substituting the pressures and substituting the A1, A2 value, we can compute it, the Q values here. That's what will come out to be. The Q will becomes 0.085 meter cube per second. So now if you just look at, we have applied the Bernoulli's equations for these problems first to compute what will be the discharge. And here, as you know it, we have considered it's a horizontal surface, so Z1 equal to Z2, that's what we have cancelled out, and we are just substituting the mass conservation equation and the Bernoulli's equations to compute what will be the Q value. So once I know the Q value, to estimate whatever will be the force component, we're going to apply linear momentum equations. We are going to apply linear momentum equations. Let us apply the linear momentum equations for these problems. And always I encourage that please start applying the Reynolds transport theorems, simplify the Reynolds transport theorems from basic linear momentum equations to the simplifications portions. That what need to be do it. So based on Reynolds transport theorems, we can write for linear momentum equations. We can write that the sum of the force is acting is equal to same part change of is equal to, since it's a one inflow and one outflow, so we'll have a beta m dash v2 beta m dash v1. So that's what is outflux, mass outflux. Sorry, this is what momentum outflux, and this is what momentum influx components. And here we can assume it, the beta is equal to the 1, and being a steady flow, again this part becomes 0 as it's a steady flow conditions. So you just have to compute the momentum flux, influx, and the outflux. That's what the net momentum outflux, what is happening through this control surface. That's what will be show us what are the force components in scalar component x direction and the y directions. So we will apply along the x directions to get it. If I apply in the x directions, you'll get it. The sum of the force Fx will be the P1 minus A1 minus Fx. So in this case, only these momentum flux components will commit. That what will be the minus rho q square by A1. Just you look it. This is the momentum flux per unit area. Momentum flux component what we have computed, that's the reason q by a is the velocity. That's what is indicating here. And this is the P1, the pressures, the A1 is the area. And if I substitute these values, then we'll get it, the Fx will be 2.94 Newton. Similar way, if I apply in the y directions, I'm not doing for the y directions detailed equations, we'll also get it, the Fy is equal to rho q v2 minus 0. By substituting this value, the Fy will come out to be 1.7 kilonewtons. So as we know this Fx and Fy value, then we can compute resultant force, which will be the square root of Fs square plus Fy square. That's the value comes out to be 3.29 kilonewton. This is what the solutions for this problem. So let us solve this another example, which is example 4, in which in this case there is a horizontal jet of the flow is a with angle theta strike on a vertical plate, and the flow distributions here it is a q naught is the flow is coming it, and at this point the flow is equal to 0.25 times of q naught value. Then we try to find out what could be the theta value when the impact flux is neglected. So if you look at this case, we can classify the flow classifications. Like the steady, incompressible, and we can consider as one-dimensional flow, even if it looks a two-dimensional, but as will be resolve the force component in x and y directions, we can make it as a one-dimensional flow component, and frictional less flow component. That means the impact losses, the frictional components because of at this vertical plate, that's what we have not considered. If that is the conditions, so first what we will do it, we'll apply the Bernoulli's equations for this case. The applications of Bernoulli's equations. To apply the Bernoulli's equations, we can draw a streamlines. We can draw a streamlines like this. Okay. That means this is my streamline. I am applying the Bernoulli's equations from this is the point 1, this is point 2. I am applying the Bernoulli's equations from these 1 to 2 as there is no frictional loss. So if I am applying the Bernoulli's equation between 1 and 2, I can have same way I can write the Bernoulli's equations here. Standard now if you look at this part, as we have the water jet, we can consider the P1 equal to P2 is equal to P atmosphere, as it is a water jet problems. Only, and it's just striking in a horizontal jet, so we can consider Z1 is equal to Z2. That what is indicate for us that B1 is equal to B2. Similar way, if I draw another streamlines from 1 to 3, this is the 3 locations, I'll get it applying Bernoulli's equations along streamline 1 to 3, I'll get it B1 is equal to E3. Now let us apply the linear momentum equations to compute it. What could be the theta value, where sum of the force acting on this net force should equal to the 0 case. That's what the conditions in this case. If you just to visualize these problems, if I consider is a control volume like this, since this is a fixed one, the net force acting on this impact object is equal to 0. If that is the conditions, we can easily apply linear momentum equations to find out at what theta value the sum of the force acting on this should equal to 0. That is the problems what we are looking for that. So I write the linear momentum equations. Linear momentum equations for the control volume. If you write the linear momentum equations, that force component, the sum of the force acting along the x directions, that what will be equal to d by dt of the control volume rho v and the momentum flux out, momentum flux in. So this is what influx of momentum flux, that is in, that is what is out. If you look at these values, as the sum of the force is equal to 0. If I put it rho q2v minus rho q3v rho q naught v sine theta, that's what, if I just substitute the q2, q3 and q naught as this, if it is a q naught flow is coming in, and this is 0.25 q naught, as the continuity equations for q3 is equal to 0.75 q naught. Okay. If I just substitute these values, then we'll get it, the sine theta is equal to 0.5. That's what indicates theta is equal to 30 degree. This is what the solutions. This is what the answers. So basically this problem, you try to understand it, that q is not given it. The velocity is not given it. We are first to find out what could be the velocity distributions. In this case, because of water jet, you can note it that by applying these Bernoulli's equations, we find out that the velocity at v1, v2 and v3 are equal. Once you have that assumptions, you substitute in a linear momentum equations to compute what will be the theta equal to 30 degree. That means you apply the linear momentum equations over these control volumes, as there is no force is exerting on this, the net force is equal to 0. That's what we are applying it and compute it, the component what we are getting it. The example 5, which is a very simple problem on venturimeters, as given in these figures, that there is a venturimeters with having the diameter of 15 centimeters is reduced to the 7.5 centimeters, which is installed on a horizontal 5 lines, and the rate of the fluid passing through this, the Q is equal to 30 liters per second. Q equal to 30 liters per second, and the pressure difference between this throat and enlarged part, that's the pressure difference between P1 and P2, as we can find out the pressure difference as given here. The pressure difference is equal to 2.45 meters in terms of the water head. In terms of the water head, we have to find out what is will be the discharge coefficients of these venturimeters. So again, we can have draw a streamline. Draw a streamlines. This case, we can take the centrally flow part, which will be a streamline part. This, and along these streamlines, we can apply the Bernoulli's equations to find out what could be the Q theoretical value. In this case, we try to find out the question numbers 5, the solutions, what we are looking at, what could be the CD value. If I know the Q theoreticals and we know Q actual as it's given here is equal to the 30 liter per second. So the basic idea is here to apply the Bernoulli's equations along these streamlines. If I apply these Bernoulli's equations, as we apply on along the streamlines, it can easily, we can write it the same form. since in this case, whatever the Q amount of the flow comes it, the Q will be the A1, V1, A2, V2, because one inflow, one outflow conditions for this control volume. So we can write Q equal to A1 into A1, V1, A2, V2. And since it is, we know the pressure difference between 2 points, that's the reasons we can easily compute this pressure difference between 2 points as it's measured it. This is what the pressure difference is measured it. That's what will be equal to, just rearranging the terms, you will get it V2 square minus V1 square. So this is given to us. In terms of Q, we can write it these values. See, if I do that part, then I'll get the Q theoretical value from this equation in terms of A1 and A2. That's what more detail after substituting this value will comes out to be A1 square, A2 square into 2G by A1 square, A2 square. This is what the Q theoretical value. That's what the Q actual is equal to CD Q theoretical value. So as the Q actual is given, thus the CD will be Q theoretical we are getting from this. You know this value of A1, A2 value as the diameter is given to us, 2.45, 2G, all the value is given to us. So we can compute the CD value, which comes out to be 0.95 for this case. So this is a very simple problems using this Benchurimeter problems where you have to apply the Bernoulli's equation, mass conservation equations, and be remember it has given it the pressure difference measurements. You need to compute the Z1, Z2 because its pressure difference measurement is given to us. So we are not looking for whatever will be Z1, Z2. Whatever the pressure difference measurement, that's what will come it, and we can substitute to compute the CD value. So with this, let us conclude the solving on the blackboard some of the gate questions. Thank you.